Hey, here's a little bonus hint to those of you who actually watch the videos. For 39, the mechanism of dehydration is an E1 reaction that forms a carbocation intermediate. In the previous video, we saw how alcohols can get activated. Well, ethers can get activated in a similar way. If we add acid to an ether, the lone pair from the oxygen is going to be attracted to a hydronium ion. It's going to grab an H+. And note here the oxygen has a formal positive charge. This makes it easy for the bromine ion, or the bromide ion that's sitting around now, to attack the less sterically hindered carbon. Here, this is the small methyl here instead of the busy side with all this crap. And as this carbon makes a bond to the bromine, it has to ditch a bond with the oxygen, so this group is released. And you get a halomethane formed and a alcohol. But that's not what I really wanted to talk to you about today. What I really want to talk to you about today are epoxides. Epoxides are three-membered rings with oxygen. Being three-membered, this is a very small ring, so there's a lot of ring strain, which makes epoxides pretty reactive, so they're pretty fun to work with. And just like alcohols and ethers, they can be activated by acid. And again, the oxygen has 3 bonds and a positive formal charge. This also makes the carbons in the ring more positively charged, which makes them more attractive to a nucleophile, such as ethanol. Now the ethanol has a choice of 2 carbons that it could attack. It could attack the more substituted carbon or the less substituted carbon. In acidic conditions such as this, it's going to attack the more substituted carbon. As a bond forms with this carbon, it has to ditch its bond with the oxygen here, and the ring is broken. But the nucleophile is added. And for those of you who are sticklers for detail, this hydrogen comes off. Maybe it's pulled off by water. If you're using a water solvent. If you're using an alcohol solvent, I guess it would be the oxygen on the alcohol that would rip off this hydrogen. But anyway, you end up with this. What we just saw was the opening of an epoxide in acidic conditions. Now, in basic conditions, there are 3 things that are going to be different. One is that the epoxide ring can open without being activated. 2, instead of seeing commonly alcohol nucleophiles, we're going to see the deprotonated form. So before we had the ethanol, alcohol, but in basic conditions that's probably going to be deprotonated, and you're going to have the oxide form. So here's an ethoxide nucleophile. It is a stronger nucleophile than the alcohol. And that leads us to the third difference, which is that instead of attacking the more substituted carbon, it's going to attack the less substituted carbon, forming a bond with it, and that carbon's going to ditch its bond, it's going to give that electron pair to the oxygen, and the ring is going to open from the other side. So after the ring opening, you get a molecule that looks like this. there's an anion here. And if you want to get rid of that anion, you can just add some acid and turn it into an alcohol.
Made with Doodlecast Pro.